Our next step in our graphing of the trigonometric functions is not, perhaps interestingly enough, working with tangent and cotangent. We're going to go ahead and now talk about secant and cosecant. It turns out that the graphs of secant and cosecant can be found, or they are based upon the graphs of cosine and sine. And the reason for that is the reciprocal relationship that secant shares with cosine and the reciprocal relationship that cosecant shares with sine. Since those functions are reciprocals, it turns out their graphs are related in a certain way. And to sort of talk through that, I want to go back to something that I hope we have experience with, back to something from a college algebra course or a pre-calculus course or an algebra 2 course. Somewhere in the past you've talked about these graphs in algebra. This graph, and when we talk about these fraction functions now, whenever we talk about our fraction functions in this course, we will assume that all factors have been canceled, that there's no factor in the numerator and the denominator in common. So we're going to assume these fractions are in lowest form. So when I say a fraction or a function that is a fraction or a fraction function, a rational function is the technical phrase, we will assume that for this semester, we'll assume that means they are all reduced to lowest form. There are no factors in common. With that proviso, everything I'm going to say is correct. If we don't have that proviso, there are some other things that can occur, but we're going to stay in the shallow end of the pool, and we're going to assume that when we talk about our fraction functions, that they are in reduced form. So you remember graphing these. We used to call these the Golden Gate Bridge graphs. What I've done here is I've taken f of x is 1 over x squared plus 9, and g of x is just the denominator function, x squared plus 9. Now, you're certainly familiar with that. These pictures are not to scale. I haven't worried about the scale at all. If this is 3, 9 should be much further down. But these are not to scale, but the basic ideas are here. We know that this is a parabola that's been shifted down 9 units. And so this brown is this parabola. And we know the x-intercepts. To find the x-intercepts, you set this expression equal to 0. If we set the denominator, if we set this x squared plus 9, or minus 9, equal to 0, that will find the x-intercepts. In this case, x is equal to 3, x is equal to negative 3. We find these two x-intercepts. But notice, this is what we used to call the Golden Gate Bridge graphs, these graphs that you made of rational functions. This actually has vertical asymptotes. And the key I want you to emphasize here, I want to emphasize this so that we see it, is that the vertical asymptotes of this graph fall precisely at the x-intercepts of this graph. And so if we want to find the vertical asymptotes of this entire function, the way we find the vertical asymptotes of this function is you set its denominator equal to 0. Anywhere this denominator crosses the axis, this function has a vertical asymptote. I say that again. Anywhere this denominator crosses the x-axis, anywhere this denominator has an x-intercept, anywhere it crosses the x-axis, this function, the entire function, has a vertical asymptote. That occurs even in this scenario. This is a simpler scenario, but the same principle is occurring. Here I have the function, which is the blue, right? This blue graph with a vertical asymptote. And then the brown, I have just the linear function, x plus 4. Where does this function cross the x-axis? If I set this to 0, I get x equals negative 4. That's where this has an x-intercept. But anywhere this function has an x-intercept, that guarantees that this function has a vertical asymptote. So the vertical asymptotes occur anywhere the denominator is equal to 0. I say again, the vertical asymptotes occur anywhere the denominator is equal to 0. Now we're going to take that, modify the language a bit, and use that to advantage when we talk about secant and cosecant. Because you can see secant and cosine have the same relationship, reciprocal, that these functions share. These are reciprocals. And so we're going to be able to leverage these ideas to be able to draw the graphs of secant and cosecant. So that's what we're going to be up with next. All right, so let's consider the graph of secant. We're going to consider the graph of secant. All right, so I'm going to say f of x is equal to secant of x. All right. I'm going to say, what is the associated function? Secant of x is associated, it's not the same thing, but it is associated with cosine of x because they are reciprocals. So this is the associated function. And in order to graph secant, the first thing you do is you graph the associated function using the same techniques we've discussed so far. So what do we know about graphing cosine? If we wanted to graph the whole thing, strictly speaking, we would go through the whole 4 steps. We would do the basic shape, right? The basic shape. What is the basic shape of cosine? Well, obviously, the basic shape of cosine is here. What is the amplitude? Right? The amplitude is absolute value of 1. Right? Absolute value of 1 is 1. What is the vertical shift? Vertical shift is there is none. I'm graphing this function now. This function, all these questions, all this information is based upon cosine, the associated function. Vertical shift, there is none. And then the standard, or we're calling it the basic interval. You can call it basic interval or standard interval. Those are interchangeable. The basic interval, there's x, and so this is 0 less than or equal to x is less than 2 pi, and there's nothing to do here, right? And so if I take this over to the graph, here's 1, here's -1, 1, 2, 3, there's pi, double that approximately is 2 pi. So the peak is at 1, the trough is at -1, the sides are at 0 and 2 pi. Here's pi over 2. Here's 3 pi. This is very standard. I don't need to make that shape. Here's where the difference occurs. We're graphing the associated function. I don't want the graph of cosine. I want the graph of secant. I'm going to use cosine as a stepping stone to get to secant. And so when you draw the graph of the associated function, in this case cosine, draw it as a dotted line. Not solid, draw this dotted. So cosine is peak, node, trough, node, peak, but draw this as a dotted curve because this really isn't the graph we're looking for. We want secant. But now we use the fact that secant is the same thing as 1 over cosine. And what we have is everywhere cosine crosses this axis, everywhere cosine crosses the axis. And when I say the axis, I don't mean the x-axis. I mean the axis, the central axis of the function. So if this is shifted, I'm talking about where are the nodes. Everywhere cosine has a node, that's why the node terminology is so important. Everywhere cosine has a node, the associated function secant has a vertical asymptote. Everywhere cosine has a node, the secant associated function has a vertical asymptote, and vice versa. Where are the vertical asymptotes of secant? The vertical asymptotes of secant are at the nodes of the associated cosine curve. And then similarly, where are the vertical asymptotes for cosecant? The vertical asymptotes for cosecant are at the nodes of the associated sine curve. That's why we sketch the cosine curve here in dotted line. It's not the picture we're looking for, but it's going to give us the information to find what we're looking for, because the vertical asymptote for secant is at pi over 2 because of the reciprocal relationship, and another vertical asymptote at 3 pi over 2. If we wanted an extra piece of the picture, where would the next one be? This is at 1 pi over 2, 3 pi over 2, then 5 pi over 2, then 7 pi over 2. These are the odd multiples of pi over 2. The odd multiples of pi over 2. Negative pi over 2, negative 3 pi over 2. The odd multiples of pi over 2. So the vertical asymptotes at secant occur anywhere there is a node for cosine. In the basic function, is at the odd multiples of pi over 2. Now, the rest of this is known by the curve has to approach the asymptote. Wherever cosine is positive, the reciprocal is positive. Wherever cosine is negative, the reciprocal is negative. Wherever cosine is positive, the reciprocal is positive. It must approach the asymptote. And look at 0. At 0, what is secant of 0? Once we understand this, and the rest of them fall into line. Secant of 0 is 1 divided by cosine of 0. But what is cosine of 0? Cosine of 0 is 1. So if we want secant of 0, that's 1 over cosine of 0. But that is 1 over 1 is 1. The reciprocal of 1 is 1. And as x gets smaller and smaller, the reciprocals get larger and larger. And so what happens is the graph, it must be tangent at that peak. And if we had the rest of the picture over here, this would, and there would be the vertical asymptote, this would look sort of like a little horseshoe. Now we don't need this piece because that's not the standard interval. But here, at the trough, again, it's a tangent point, and then it approaches the asymptote in this direction, approaches the asymptote in that direction. This is supposed to be nice and symmetric. My picture is terrible, but that's the basic idea. And then this is tangent, and it approaches this asymptote. If we had more of the picture, the same thing would happen over here. So if all we need is one period, that is one period of the graph of secant. We get half. They look sort of, they're not actually, but they look sort of like little horseshoes. Sometimes students describe them as little parabolas. They are not parabolas. They have asymptotes. But it's this half of the top, because we're cutting it off halfway. It's the entire horseshoe, if you will, at the bottom, and the half of the curve at the top. If we had the entire cosine graph, then we would have an entire set of these. Below, above, below, above, below, above, below, above, following the graph of cosine. And so this is the graph of one period of the secant curve. The standard period for secant is the same as the standard period for cosine, which is 0 to 2 pi. The amplitude of secant is 1. So anytime you want to find the graph of a secant function, you graph the associated cosine function, dotted line. Anywhere you see a node, that becomes an asymptote for secant. Node here, asymptote here. And then the tangent points are at the peaks and the troughs. The peak and the trough of cosine are the points of tangency. And then you sort of fill in, roughly speaking, the rest of the curve, making it a rough approximation. This is a terrible picture. It's supposed to be nice and symmetric, but my picture is bad. All right? And then precisely, it's not even worth going through the same argument, because the precise thing happens here with cosecant. Anywhere sine has a node, that's where cosecant has a vertical asymptote, and then you play the same process for it. So anytime you want to graph any function of secant or cosecant, you first graph, dotted line, the associated cosine or sine function using precisely the same procedure we've done before. And you make this nice little dotted line curve inside this little box. But then essentially what happens is it explodes outward. And anywhere that has a node becomes a vertical asymptote, node becomes a vertical asymptote, the peak becomes a point of tangency, the trough becomes a point of tangency, and you sketch in the graph from there.